Hello, welcome to the tutorial video for Math Focus Quizzes 2 and 3 Basic Counting. This is the kind of thing like how many outfits can Sally make, how many ways can this dice roll, stuff like that. This is a relatively simple concept. How complicated it gets is really up to the problem. There's no formulas to memorize or anything, but there is a kind of logic you need to keep in mind. I like to think of it in terms of slots to fill and number of choices within those slots. All right. So, for example, let's say we are rolling 2 dice and we want to know how many different combinations, how many different possible dice rolls can we get if we roll 2. So we have 2 dice. Technically this is not a combination, that's another thing, but I don't think y'all even have to worry about that in this year's math, so I can use that term right now. Don't get used to it though. So we are rolling 2 dice, right? And we want to know how many different possible outcomes from those 2 dice rolls we can get. So for the first dice roll, I'm assuming 6-sided dice, we have 6 possible outcomes, right? 1 through 6. And for the second one, we also have 6 possible outcomes. So if we roll 2 of them, taking into account the order, so 1 and 1 is different than 1 and 2, different than 2 and 1, stuff like that, we have 36 possible outcomes. How many different ways can you roll 2 dice? The answer is 36. This can also apply to something like coins. So let's say we're flipping 3 coins and we want to know how many different ways can that happen. All right. So we're flipping and there are only 2 options, right? So we have 3 slots. We're flipping 3 coins. And so I put down my 3 slots. And every coin only has 2 choices or options, possibilities, different words for that, that can happen. So we flip 3 coins. There are 8 ways that can resolve. If you made a list of all the different ways it could happen, it would be 8 long. You'll get some of these kinds of problems, but more commonly you'll get things like how many outfits can Sally make? Let's say she's choosing just a shirt and pants. Make it simple. So those are our 2 slots to fill. We need a shirt and we need pants. And let's say she has, in her very limited closet, Sally has 5 shirts and 3 pants. That means that the total number of unique outfits that she can make is 15. Pretty simple stuff. If you've taken a tax test, you've done this kind of deal. They can make it more complicated mostly by throwing in logic to it. So as I go through the problems I have put in this PowerPoint, I've tried to touch on the different ways they can complicate this sort of process. All right? So this one is really simple. Johnny has 7 shirts and 4 pairs of pants. How many outfits consisting of 1 shirt and 1 pair of pants can he make? I can type. Just like that other example I did over there. Got our 2 slots. Multiplication. 7 shirts, 4 pants, 28 outfits. Not that crazy. A bag of marbles contains 25 numbered marbles. So this is another very common type of problem you'll get. This is about as simple as this type of problem can be, where you have some pool of things. In this case, there's 25 marbles. And you want to know how many different ways something you can do with that pool can happen. All right. So we are choosing, or we have 2 slots because we're seeing how many different combinations of 2 marbles can be made, assuming no replacement. All right, so we're going to take a marble out, and then we're not going to put it back in. So that means for our first marble, we have 25 choices. Right? And for our second marble, we've taken one out, so we only have 24 choices. So your answer is going to be those multiplied together, which I'm not going to do off my head. You don't really need the calculator for this. But you need it for this thing, but you don't need to do any special functions. I can't do that in my head. Regardless. Pretty simple type of problem. Shouldn't throw you for a loop, but they will take this and they will add things into it. And you have to be comfortable with this concept, extremely comfortable, because they will essentially write trick questions for it. So, this one's kind of tricky. How many 3-letter words, so we're filling in 1, 2, 3 slots, all right, can be made using only the first 12 letters of the alphabet, given that adjacent letters cannot be the same. So you have to think about this one. There's no golden rule for when adjacent things can't be the same. So we'll just start with the first one. That's generally what you do, is you look at your very first choice, and then you go from there. If any logic applies, so remember when we took out the marble, 25, logic changed what went in the second slot. So in this case, for the first letter, we have the choices of any of the 12 letters. And then we need to look at the second one. Now, it says that adjacent letters cannot be the same. So, we're not messing with this letter yet. So just looking here, this letter can be any of the 12 except whichever one we chose for that one. So we have 11 total choices here. For the third letter, we are choosing again based on the other two options we've already done. So it cannot be the same as the one we chose here, but it can be the same as whichever one we chose for the first one. So if we did A and B, this last one can be A again. So this also has 11 choices. And you just have to think that out. Ones that require that level of abstract thinking are not terribly common. But just when you have no idea how to do it, just with these counting problems, stay calm and try to literally speak it out. Try to think about it in words. That always helps me. And then this, I'll do this. I might as well. So over in the calculator, that's the total number of 3-letter words you can make with no adjacent similar letters. Cool. Okay. At a very limited jukebox, a customer can choose from 4 Nickelback songs and 6 Red Hot Chili Pepper songs. So your total library is 10 songs. In how many ways can a customer play all of the songs if they begin with the Nickelback song and end with a Red Hot Chili Pepper song? All right. So if we're playing all the songs, and there are 10 total ones, we have 10 slots. I'm not spacing these out very well. That 10? Yep. Okay. So, we are going to think of these logically, and I'm going to start with the first one, but because one of our stipulations is that the end has some restriction to it, we're going to look at that one second, and then we're going to mess with the rest of them. So, looking at the first one, if we're beginning with the Nickelback song, we only have 4 Nickelback songs to choose from. So, we're going to put 4 there. And then it says we end with a Red Hot Chili Pepper song. So at the end, we have 6 choices. And then we look at the rest of them. So for all the rest of them, we can choose any of the remaining songs. So we've already chosen 2 by this point out of our pools. And we have 8 total left. And once we've chosen that one, we have 7, 6, 5, 4, 3, 2, 1. If they said that it just had 10 songs, right, and it was like, how many ways can you play those 10 songs, it would just be 10 times 9 times 8. It would be 10 factorial. 10 times that minus 1 all the way down to 1. But because they've added these stipulations, it changes the problem drastically. So the answer to this one is 4 times 8 factorial, which is that 8 times 7 times all the way down to 1 times 6. And it's a lot. It's a whole bunch. And that's why you need a calculator. A kindergarten class of 22 students must choose a line leader, flag carrier, and box holder. If no student can have more than one responsibility, how many ways can the positions be filled? So this is kind of similar to the marble problem. This is the simplest kind. It can get more complicated, but we're looking here. Okay, so we have 3 positions to fill, 3 slots. 1, 2, 3. We have a pool of 22 options for to fill these 3 slots. So for our first one, we got 22. Second one, we've already chosen a kid, so we need to choose one of the other 21. And the last one, there's 20. So that's how you get your answer. Pretty easy. This one. Okay. So sometimes the stipulation that they add almost removes... It's a tricky thing. It almost doesn't matter, in a sense. I'll show you. So we're flipping a coin 5 times. Fair coin just means it's going to be 50-50. Calculate the number of ways in which the first flip is heads. So we're flipping it 5 times. But we've got the stipulation that the first flip is heads, which all that means is that for our first flip, we only have one option. Now, when we multiply this all out, that's why I was saying it almost removes this. And this could go for any of them. So if it said calculate number of ways in which the third flip is heads, then you would also have to put a 1 in the third one. If it said the first, third, and fifth, you'd put 1, 1, 1, and the 2s for the fair coin would only go here. For this one, we're looking at when the first flip is heads. So the rest of these are 2. And the answer is 16. Were this question, how many ways can a fair coin be flipped 5 times, and there were no stipulations, the answer would have a 2 here, and it would be 32. So that's how it changes that. And they would definitely have 32 as an answer choice for this particular problem. So that's why you have to if you just think about these things and stay relaxed, that's your best bet. Okay, Bill is going to a pizza place. He can choose 3 types of crusts, 6 types of meat, 4 kinds of veggies, and 3 types of cheese. He can also choose to have no cheese, meat, or veggies, and that's important. That's the only thing that changes this problem from the normal outfit problems. Assuming Bill can only choose one option in each category, how many pizzas can Bill order? How many different pizzas? So, we are choosing crust, meat, veggies, and cheese. So that's 4 spots to fill. And we can have 3 types of crust, 6 meat, 4 veggies, and 3 cheeses. However, you can also choose to omit any of those. And all that means is that we add 1 option to each of these spots to fill. So for the meat, he actually has 7 options because one of them is none. For veggies, same thing. And for cheese, same thing. And then we'll multiply this out. And wow, cool. Haha. That's our answer for this particular problem. I believe this is the last unique one. Basic counting's pretty simple. You just got to get used to it. They'll continue to make it more complicated. On an actual state test, on a regional any of the actual competition math tests that are cumulative, you'll only have maybe 2 or 3 problems about basic counting because the harder things are in other categories. Still very important to get those points though because they're so easy to get usually. So, Joni can make 924 outfits with her wardrobe. Each outfit consists of 1 top, bottom, and shoes. So we're filling 3 slots. if Joni has 12 tops and 11 bottoms, how many shoes does she have? So the number 924 up here is going to be what normally would be our eventual answer. We know she has 12 tops and 11 bottoms. So we're looking for this slot here, and it's basic algebra. So 12 times 11, I believe, is 132. Yeah. So then we're going to take that 132 times some other thing equals 924, and we'll divide it out. And it's 7. She has 7 total options for shoes. So that would be your correct answer choice. That's as complicated as these problems get. They can add stipulations into things like this. They can mix and match the different twists they can put on a counting problem, but that's about as hard as it gets.